Okay, so you are welcome to this lecture. Today we want to look at some calculations on pressure measurements. Don't forget, this is Electro Teach channel. That is the channel for teaching, instrumentation, computer, electronics, and mathematics. The channel handle still remains youtube.com/@electro_teach. @electro_teach. Today we are looking at pressure measurements using manometers. I want to explain how that is done and solve one or two problems. So if you have not done so, I want to remind you to please subscribe to the channel at electro_teach. Subscribe to the channel and like and share the video so that other people may also receive a notification about the video and watch it. And when we post new videos, YouTube will be notified by YouTube. Now let's look at the theory behind the measurement of pressure using manometers. Now, when we want to measure pressure using manometers, when you look at the screen, you see the theory of that. The manometer is a device used to measure pressure, and then it uses relationship between change in pressure and a change in elevation in the static fluid. So when there's a change in elevation, then there will be a change in pressure in the fluid, and that is expressed as the formula you see on the screen here. Delta P equals gamma H. Delta P equals gamma H. Delta P is a change in pressure, and H is a change in elevation. That gamma is specific weight of a fluid. So when you look at the figure now, the figure we have here, it demonstrates how to use a manometer to measure pressure. See a sketch of the manometer, the typical manometer, which is like a U-tube, and then it has a bulb at one side. Then the manometer is filled with a gauge fluid. The gauge fluid could be either mercury, aqua, probably sometimes another liquid as a gauge fluid. Now, as we have it here, there is water. The water is in the bulb on the left side of the manometer. Then the gauge fluid is mercury. Then we have air above the mercury, and the air is at atmospheric pressure. Now, this is a typical structure of the manometer, ordinary manometer. It's different from the differential manometer. So we can use either water, mercury, colored oils, alcohol, and so on and so forth as a gauge fluid or manometric fluid. Now, when the manometer is put to measure the pressure of the fluid, under the action of the pressure to be measured, the gauge fluid is displayed from its partial position. And because the fluid is in the manometer is at rest, then we can use the equation delta P is equal to gamma H to calculate the unknown pressure. This is supposed to be gamma H, not delta H, but gamma H. This one's supposed to be gamma, something like this. So this is what is going to be used. The formula is going to be used to do the calculation of the pressure measurement throughout, the manometer, and then it will be summed algebraically to actually give the unknown. For example, looking at this gauge fluid inside the manometer, the gauge fluid is mercury. We have water here, and then air above the mercury column at atmospheric pressure. The air is at atmospheric pressure. Now, looking at that, we want to compute the pressure of water at the point A. We want to compute the pressure of water at point A. So let's look at the solution. The pressure at point one up here is the atmospheric pressure. and that is known. That's atmospheric pressure, and that is represented as a pressure P1. It's represented as pressure P1, and then that pressure is higher than it's on top of the pressure inside the mercury. Now, within the mercury, the pressure that exists within the mercury about 0.25 meters below the air can also be calculated, and that is calculated by adding it to the value of the pressure at 0.1. So P1 plus gamma m times 0.25 meters. In order not to get confused, let's remove this m here. The calculation is a meter. The subscript m here indicates mercury. So gamma m times the distance, that is gamma of mercury times 0.25 meters. Whatever you get there is a level of pressure that exists from 0.1 to a depth of 0.25 inside mercury. That is calculating the pressure that exists from top up to that point. So we had everything up together to be P1 plus gamma m plus 0.25. So the two of them will be added together like that. Now we go ahead to now look at the pressure at 0.2. Now pressure at 0.2, that is the level that we reach now, 0.2. The same pressure, exists at 0.3. 0.3, if you look at the manometer up, you see 0.3, see 0.1, 0.2, 0.3. So 0.3 is the one on the left hand side of the manometer. Take notes, to start calculation in this case, you start from the vertical side of the manometer, from the vertical, parts of the manometer, and then be calculating the pressure from point to point up to, then you turn around and calculate it up to the bulb area of the manometer. Now, the pressure at 0.3 will be deducted from what we have obtained from 0.1 to 2 that we have added earlier. Why? The reason is because as you turn around the manometer, the pressure at the left-hand side of the manometer is reduced. The pressure at the right-hand side of the manometer is reduced. So therefore, the pressure at 0.1 is obtained as, when you look up now, you see 0.3 rather. The pressure at 0.3 is equivalent to P1 plus gamma mercury times 0.25. Gamma mercury times 0.25. That is what we obtained earlier. Gamma of mercury times 0.25. Then gamma of mercury times 0.25 plus P1, which is atmospheric pressure, minus gamma of W times 0.4. The distance from point 3 to 0.4 is 0.25 plus 0.15. That is the total distance. So that is the height that we are taking into consideration while the fluid is water. So 0.4 multiplied by gamma of water is another pressure that we are getting from 0.3 to 0.4. That pressure is going to be subtracted from what we have obtained from 0.1 to 0.2. And that's what we have here. So what we obtained earlier is P1 plus gamma m times 0.25. Now we can now say minus gamma of water multiplied by 0.4 meters. 0.4 meters. So we can now simplify this and determine the final answer. Now the gamma at the pressure at 0.4 is the same as at point A that we are looking for, because these are the same level inside the same manometric fluid, which is water. The 0.3 is below and is equivalent to 0.2 because they are at the same level within the same manometric fluid, which is a mercury. So 0.4 is the same as 0.8. So if you simplify that one out now, we get PA equals P1 plus gamma M times 0.25 minus gamma W times 0.4. We know that P1 is atmospheric pressure, so it is equal to 0 Pascal gauge. 0 Pascal gauge. It means the final answer we are going to obtain now will be gauge pressure, to be gauge pressure. S we will not represent atmospheric pressure as 0 Pascal if it's not going to be gauge pressure that we are going to obtain. So gamma of M is calculated. Gamma of W is also calculated. Gamma of M is 3G times 9.81 kilonewton per meter cube. So that gives us 13.54 times 9.81 kilonewton per meter cube. All right. And that is 132.8 kilonewton per meter cube. Then gamma of water is 9.81 kilonewton per meter cube. All right. So the two of them, we have the two of them now. We can now substitute the two of them into the equation up here, to this equation, to know the value of PA. So PA will be equal to P1 plus gamma M times 0.25 minus gamma W times 0.4. So that is 0 Pascal plus 132.8 times 0.25 minus 9.81 times 0.4. So that is how we obtain the value of the pressure at point A. So if you simplify that, we are going to get 33.2 minus 3.92 kilonewton per meter cube, per meter squared. Kilonewton per meter squared. So that is what we obtain. So that is it. And the answer is 29.28 kilonewton per meter squared. Gauge pressure. Gauge pressure. All right. So we want to check the solution for the differential manometer. So let's check the solution right here. The differential manometer problem is here. We have point A and point B. Point A is on the vertical side of the manometer. Point B is on the horizontal side of the manometer. And we have three different manometric fluid. We have two different manometric fluid, but they are in three sections. We have oil at the vertical side. We have water at the UU section. And then at the horizontal bulb, we have the oil again. Then the distance from point to point is indicated, the height from point to point, from point A to point 1 to point 2 to point 3, the distance is indicated. Now the pressure at point 1 is PA, and the pressure at point B is PB. Now P1 can be calculated by determining the height from point A to point 1, which height can be determined right here. If you look at the screen, you see that we have 0.11 plus 0.75, that is 0.86. So 0.86 multiplied by the gamma of oil. 0.86 multiplied by the gamma of oil give us the pressure, at a point 1, plus the pressure at point A, which is not known. We don't know the pressure at point A right now, so we add it together to the calculation. All right. So we look at the solution here. We have P1 equals PA plus gamma of oil times 0.86. That is the height from point A to point 1. That is the pressure at point 1. Or let's say the pressure at point A. Pressure at point A. That's the total pressure at point 1. The pressure at point A plus the pressure at point 1 added together to give us a P1. P1 equals to PA plus gamma oil times 2.86. Now, gamma oil is specific weight of the of oil, which we are going to determine soon. Now, the pressure at point 2 is the pressure at point 1 because they are the same level in the same manometric fluid. That is point 1 and 2. There are two points at the same level inside water as manometric fluid. Now, pressure at point 2 is equal to pressure at point 1. That is it. P2 equals PA plus gamma oil times 0.86. Now, we want to determine pressure at point 3. Pressure at point 3, we have now turned around the manometer. We are now moving up. So whatever we are going to obtain will be subtracted from what we have obtained up to point 2. So the pressure at point 3 will be calculated as P3 equals P2 minus gamma of water times 0.75. The manometric fluid now is water. So, and the height is 0.75. So we subtract whatever you have there from what we obtain up to point 2. And then that will be equivalent to PA plus gamma of oil times 0.86 minus gamma of water times 0.75. Now, to determine the pressure at point 4, pressure at point 4 will now be another distance covered with the 0.11, and then the pressure we obtained there will be subtracted again from what we have obtained earlier. The distance is 0.11, so that pressure at point 4 can be calculated as PA plus gamma oil times 0.86 minus gamma W times 0.75 minus gamma of oil times 0.11, because that section now has oil as the gauge fluid. So if you simplify this, the pressure at point 4, which is actually pressure at point B, can be expressed in terms of pressure at point A like this. PB equals PA plus gamma of oil times 0.86 times gamma of water times 0.75 minus gamma of oil times 0.11. So if you simplify it, you can bring PB minus PA together on one side of the equation to have on the other side of the equation gamma oil times 0.86 minus gamma of water times 0.75 minus gamma of oil times 0.11. If you combine the like terms, you see that we have gamma of oil twice now. So we will have a simplification as we go on. But now let's calculate the gamma of oil. Gamma of oil is Sg of oil times 9.81 kilonewton per meter cube. That is 0.86 times 9.81, and that's equivalent to 8.44 kilonewton per meter cube. The gamma of water is a constant 9.81 kilonewton per meter cube. Then we can determine PB minus PA. PB minus PA equals gamma of oil multiplied by 0.86 minus 0.11. That is collecting like terms, minus gamma of water times 0.75. And that gives us gamma of oil times 0.11 minus gamma of water times 0.75. So it's very simple. So we can now substitute the values for both gamma of oil and gamma of water that we have calculated just now. Then that one will help us to determine the value for the PB minus PA. So if you simplify that, we have PB minus PA is equal to 0.75 gamma oil minus gamma water. 0.75 times 8.44 minus 9.81 kilonewton per meter cube. And that is 0.75 multiplied by minus 1.37. And the answer is minus 1.03 kilonewton per meter squared. Minus 1.03 kilonewton per meter squared. A negative sign here means that the pressure at point A is actually higher than the pressure at point B. So in other words, if you want to determine pressure as PA minus PB, the answer will be positive 1.03. Now, take note that we do not know the value of PB, neither do we know the value of PA. But the manometer is actually a differential manometer, so the difference between the pressure and the 2 points is what we have determined as minus 1.03 kilonewton per meter cube. So the negative sign is just to tell us that the pressure at the point A here is higher than the pressure at point B. So that is it. So you can go this in order to actually familiarize and master the solution. So that is it. Thank you for watching. We want to see you in the next video. So I want to see your reaction to this video. Comments, Let me know your reaction. I will respond to your comments at the comment section. Don't forget to subscribe to the channel, like and share the video. See you during the next video. Thank you.